I'm happy to be here. Thank you, Dirk, for the invitation. When I reviewed the program, there are kind of quite some names when I was a young person, I was kind of reading papers from. Some are here, some are kind of maybe online. So it's a cool time to be here. Thank you. Okay, so what I will do today, so I'll do a bit of thoughtful process and complexity science of it, although I believe I'm not too old, I can do some things on it. Say some things on the limitations, because Dirk at the intro of this workshop has what we can optimize, what we cannot optimize for. And then I would not to be just, let's say, theory on the commentatory side, I want to kind of go a little bit to the research. So because some of you, a subset, is eager to see some equations. So I have prepared some things there. And then I would want to see the concluding remarks. Okay. Let's start. I think that kind of complex systems kind of most probably were defined a few times during this workshop, if not systems that are composed of large number of agents that are interacting non-linearly. There is some type of spontaneous order of self-organization. We can see here something that represents chaos, some type of community structure, some type of social processes that are happening, some people that are able maybe to be the market with respect to if we say that the market, financial markets are complex systems, and I do believe that they are complex systems. And there is one funny cartoon that I always use based on the herding on markets, how people are reacting or underreacting on certain events. Okay. So to prepare for this workshop, I ordered some of the books. I don't know who of you has seen the series from Santa Fe and the foundational papers of complex systems. Yeah. Okay. Maybe some of you have read. I have prepared this 2,858 pages. I've tried to cover it for this presentation. I'm kidding, but I've passed through majority of these things, and I was trying to search for some of the connections with respect to today. I found two connections. For example, you will hear, for example, Joe Farmer is going to be speaking on Friday, if I'm not mistaken. So he has been involved in having some of the foundational papers, like on a paper that's called Rosetta Stone, where he is connecting different type of connectionism, neural networks, immune theory papers and theories together. Okay. Now, these people, I will also be a bit walk because it's still a small room. They did kind of quite a big work. They even kind of, I don't know why, for how long they were writing it, but they say the forefront that 14 colleagues are gone that were involved. I don't know, maybe in collaborations. I'm not sure whether in picking, but yeah. This is one of the introductory slides when they're talking about the progression of this, let's say, complexity thoughts that had all sorts of different names, cybernetics in 60s, 70s. As you can see here, for example, people that are doing the type of talk is machine learning and complexity. So you see here pioneers like Turing, you see Kolmogorov for algorithmic complexity, Shannon information theory complexity. You see some people that are believed to be fathers of neural networks, etc. Okay. Modern version of how neural networks are also created is kind of this timeline. Some of the very important people from McCulloch, Pitts, Rosenblatt, Minsky, people that were kind of involved in creating the backpropagation. People that did convolutional neural networks, and then also one particular person, Schmidt-Huber, that is currently here in Switzerland, that also is telling another type of a story that I will mention at the end. Okay, the thing exploded, started to explode in 2012-14 with AlphaGo, PyTorch, AutoGrid, and it's really different type of framework. So I can say that PyTorch stuff is differentiable programming. People that were able to propagate through through differential equations, winning Turing awards, and then of course like getting AlphaFold and also GPT. Okay, The second tail that hasn't been shown usually is another type of authors that were kind of, usually they have done many of these things a little bit prior, like Fukushima, Mari, or Ivanenko. And today, actually, I will just show you one part of Alexei Ivanenko. The reason why he's not shown, and actually he is also forgotten even in these Santa Fe foundational papers. His paper from 1971, when you start to read it, it says, for example, modern control theory based on differential equations is not adequate tool for solving the problems. And then he's actually proposing a theory that has the name polynomial theory of complex systems. And it's actually, it's based on the data, and he proposed how one with self-organizing principle, it's possible to create deep neural networks. At that point in time, they have polynomial type of activation functions. They were kind of, they had an arbitrary depth. And he had a kind of a mechanism how to control this depthness. And it was created in 70s. It was under this codename group method of data handling. So that's the reason why this type of neural networks also have a name, GMBDH, neural networks. Okay. So yeah, very nice work from Santa Fe, but somehow this guy was again forgotten. So I tried to mention him because it is to a certain extent important. He's also regarded as a father of deep learning. Now coming back a bit to the science again, showing here Richard Feynman. And I like this observation from one of his lectures. It goes saying like, it actually goes, you know, to the story of if someone is able to predict, is this enough? You know, and he's comparing it to the Mayan astronomers, because I remember also a few years ago, there were one email circulating, why are ML people taking all of the jobs from scientific disciplines? Okay, so I will address this at the end. So what is connected to the Mayan astronomers was that they were able to actually make observation and even accurate predictions, you know, where is going to be eclipse, when certain stars are going to be at certain positions, and they were accurate at forecasting. But they could count, but they were not aware of the physical laws that govern the celestial mechanics. Okay. And it's kind of an interesting thing when one is dealing about the paradigm of computation, that you can be accurate, but it doesn't mean that you actually are understanding the governing laws. Okay. The first principle of nature and also physics is least action principle, where which kind of boils down to taking trajectories that minimize the path of least action. So one usually writes some type of Lagrangian, and then writes this type of Lagrange equations. And then the question is, you can derive actually second Newton law from it. You can be also going to quantum mechanics, particle physics, and general relativity, just writing different Lagrangians, and you can be deriving all sorts of nice laws. Can we use it to derive the second Newton law for social system? Not so much. I also discussed this at one point. Some people, so the claim is currently there is no single fundamental principle that governs the complex systems, like a least action. Of course, but there are more kind of combination of principles from game theory, economics, social science. Although some economists would argue, for example, bounded rationality, that's a fundamental principle that governs economics, for example.
But, I was told better use the mic for the internet. So.
Okay, thank you, good. Okay, then doing a little bit continuing and making a few notes on what we can optimize for, what we cannot optimize, and what are the limits. And as I've showed, let's say, some of the fundamental principles from which it's possible to derive the governing laws, at least in physical systems, what happens when you try to extract dynamical equations from experimental data? Okay, it is known, it has been shown, this is a PRL paper, that these type of problems are NP-hard. Okay, what is an NP-hard? Kind of in 70s, Karp had a very nice seminal paper where you are able to kind of connect one type of a problem, reduce it to a different type, and essentially you have something like free set problem that's considered the hard problem, and then you are doing reductions. Okay. For example, in practice, what does it mean? One of our papers that when I was at Dirk's place that we did at PNAS published, like network dismantling, it's a problem of that is an NP hard, how to actually dismantle a structure. I know that Professor Shlomo Havlin also has a few papers there. But nevertheless, it's not prohibiting us. You know, when someone says problem is an NP hard, people usually don't say, okay, I give up, okay? It just means asymptotically you cannot have kind of algorithms that are able to scale with respect to the problem size. So this is, let's say, computational complexity approach. And there is all sort of zoo for computational complexities, how they fit to this picture. So although some things are NP hard, it doesn't mean that you are not able to approximate. So there are, for example, problems that are admitting fully polynomial time approximation schemes. What does that mean? It means essentially that you can pick for certain instance of a problem, parameter epsilon, and then you're able to get an output, and you are able to have some type of a bound, 1 plus epsilon, or yeah, maybe it should be here 1 plus minus epsilon of the correct optimal solution, okay? Now, there are different type of problems, polynomial time, and also there are kind of type of problems that are called APX hard, which means that even if you want to approximate them, they become hard again. So some problems are really, there are limits how much we can solve them, and for some type of a problem, you have proofs that you will not be able even to approximate them beyond certain constant factor. Let's say for vertex cover, factor of 2 from the optimal solution. Okay, now continuing talking about the limits. For example, there are also limits of inference that people in statistical, for example, Lenka Zdeberova is studying using statistical physics, where essentially it's they're studying what happens when one is having number different type of thresholds with respect to the ratio, number of variables that one needs to estimate versus the number of observations, okay? And then you can be in easy mode, so that would be kind of you have much larger number of observations. Then you can be at impossible mode with some known bounds, and with the statistical inference here, and it's called cavity type methods. They want to actually push the boundaries of statistical inference, you know, from easy types here, and they're studying different types of phase transitions there when the problems are becoming hard. Okay. One practical paper when I was a PhD student that I worked on from PRL is essentially also it has a limit on the inference. So, for example, the detection of the patient 0 from the snapshot of epidemic spreading. So for these type of problems, there are kind of known boundaries, there are known limits. When can you actually infer who is, for example, the patient 0? And there are some kind of, you can be in maximum entropy or low entropy mode when you can detect it. Okay, and this type of problems, for example, from computational point of view, they are in a class of Sharpie complete problems. Okay, also very interesting thing, for example, for community detections that is quite useful and in general, quite powerful tool, description length, okay? Which says essentially we have two parts when we wanna, let's say, feed the data. We have one part where we are showing what is our error, okay? Of course, we are here kind of showing this, and it has a connection to algorithmic complexity, Kolmogorov complexity, with respect to number of bits that's needed to encode a data when we know the parameters of a model. And we have another part that's connected to the complexity of a model. How much bits do you need to encode the parameters of a model, okay? And now that's also one fundamental principle. For example, you are seeing some graph, and by changing a model, Erdos-Renyi, configurational model, planted partition model, and all more corrections, you are able actually to compress, and there is, of course, again, some impossible range, and here it would be a true model, okay? So I'm putting this as also a quite powerful tool. It's, one can think of it from statistical perspective, it's, you know, posteriori description of a system when you have your priors and you have your likelihoods. Okay. And now the part kind of to go to a bit more details science with respect to formula is generalization of neural networks for complex network dynamics. So the question here, it has recently been published with a colleague Vaiva, who was also at the same chair at Communication Physics Journal. The problem is, can we efficiently represent and code differential equations, but right-hand side, we want to learn with neural networks. Okay, that's a problem setting. You can have, all sorts of different type of system, autonomous system, non-autonomous system, for example, systems like that can be translated to the stochastic differential equations like Langevin equation, Brownian motion. And neural networks are helpful in three ways. For example, one can be searching for data-driven solution. So you don't know, for example, how to solve it, but you know the functional form, and you can use neural networks to find a solution. You can use it to control dynamical system, like say controllability. One paper that we did jointly with Thomas and Lucas was published in Nature Communications, essentially where we plug a neural network to control the dynamics on complex networks. And the thing that I want to talk today in 5 minutes is data-driven discovery. So if you don't know differential equation, can you learn it from a data? There are kind of different previous ways how one can study it, let's say through regressions, where you are essentially encoding different type of interactions that can happen, and then you're doing a regression. But what we want to do here is we want to do it with a neural network. Okay, we know that neural networks, now coming back to the limits of, or what we know about machine learning, with universal approximation theorem, we know neural networks are universal approximators. So for sure they can approximate everything. But now there has to be some catch. From statistical learning theory, we know if we have the same distribution in train and test, we have some bounds that we can actually then be applying this type of systems. And let's say what is the problem with this? Let's say you have three-dimensional system, three type of agents, and you want to learn the differential right-hand side of differential equations, so you can have samples from three agents. Here you have derivative, okay? And you can learn this now. But what happens when you now want to apply this type of a system on an agents that it hasn't seen, like hundreds of agents? You learn it on three. What happens when you go on hundreds, okay? What we do is that we separate the differential equation to two parts, self-interaction, neighborhood interaction part. Neighborhood interaction part, we are using graph neural networks that are encoding network structure, okay? And this is kind of the main result that we have. When you're using multi-layer graph neural network or even feed-forward neural network, and these are the samples that you do, and now you're trying to see your face portrait, how well are you learning the derivative, you see what has been learned versus the true one, you are quite off, okay? Generalization in that part of the space is quite off. Of course, here, where it was, in the in-domain, it's good. But when you do appropriate inductive biases, you are able to go out of the support, and that's what we were doing. Nevertheless, we also have a type of a statistical check, so that when you go out of the comfort zone, or statistically when you don't have confidences, that you're able to know that now neural networks are not anymore describing the dynamics of a system. How? You train an ensemble of neural networks, you create some type of null distribution, and then you're able to see for a new sample, are you, in the tail of this distribution or you are not, and the statistics that you're measuring is a variance. So if different type of neural networks are having disagreement how to estimate the derivative, then you would have somehow a low confidence in it. It's connected to something that we call over-parameterized ansatz, and we are able actually, to go to out of distribution. When you change a distribution that you on which model has been trained, you are able to do well. When you go out of the domain, this statistical test can tell you, something is off. Now you learn it, for example, on size, differential equations of size 100, and you apply it on all sorts of different sizes, and it works with the same type of an error, okay? Which is kind of good.
we are able actually to also correct the statistical test, because when you're, for example, changing the ensemble, then actually the average degree changes, and you're actually able to correct this null hypothesis, such that from the upper rejection rate, you go to this lower rejection rate, which means that somehow you have better power in a test. With respect to other state-of-the-art graph neural networks, you see out of distribution what are the state-of-the-art neural network, for example, what is the error versus ours. So it's one order of magnitude better because the inductive biases are one. Okay, in the last few minutes, why is machine learning a sledgehammer that takes money from other disciplines? You are also seeing, for example, here all sort of diffusion-like processes that it's able to generate. You have now papers in reviews of modern physics, machine learning, and physical sciences that are not just telling that machine learning is used to create nice pictures, but you're actually able to solve, you're able to solve really hard problems. You can also see that there is some type of a transition this year. Nobel Prize winners, you have here Nobel Prize winner in complexity, Nobel Prize winners that are connected to machine learning. And where the whole field is going, essentially post-GPT mode, you have all sorts of advancements in the modeling, like, for example, autonomous agents, where we, for example, can analyze with this type of systems. We can have financial co-pilot that's able to reason in financial domain. And finally, there is two kind of lessons. Miha Belkin, very famous in deep learning, he's actually comparing this, that's kind of a very moment after Copernicus and Darwin, that it's actually past the last frontier, that we are able actually to model statistically what we were believing is some kind of property of humans with very basic statistical models. And the bitter lesson is that kind of more computation is better than more kind of a modeling, mathematical modeling. But again, there are kind of all sorts of different type of limits what this type of technologies can do and cannot do. And for a final one, I would say Pandora box is open. Despite its great promises, one still needs to be aware of the danger of the modern AI to society. And I would say, you know, these two things is wealth inequality and AI safety. But if one just wants to bet that these type of systems are not going to succeed or will be closed, will be contained, that's why I'd use this sentence, Pandora box is opened. Thank you very much.